Hi, this is the third video in TinyML Specialization series. In this episode, I'm gonna show you how to implement a wake-up word machine learning model on a microcontroller. Since this is a comprehensive topic, I will build step by step. Today, I will start with the first component, creating a voice interface with STM32. I will walk you through the process of recording audio in WAV format using STM32 and DFSDM peripheral, which we will use this one as an input for our machine learning model. In upcoming videos, I will cover the full end-to-end implementation from STM32 microcontroller to design a voice recognition model in Python, and finally covering the model so it can run directly on the microcontroller. Let's get started. Let's talk about the main goal of this project. What we wanted to do is design a machine learning model that can understand certain words. In this project, we will be focusing on 12 specific words. Example including yes, no, go, up, and several others. Now, why this is important? A great real-world example or application of this idea is something we have already seen in the devices like Alexa or Siri. These systems are always listening for a wake-up word, for example, Hey Siri or Alexa. Once the device hears a specific word, it will wake up the entire system and get ready for take some action. It depends on how we configure the system, like turn on the light or turn on the TV and so on. And this is exactly the type of system we will be building here. Starting simple, but with the same core idea that power modern voice assistants. To design a TinyML project like this, the best approach is to first prove the concept and test the performance of the voice assistance model on the PC or laptop, and then later convert it to a format that can be run on a microcontroller. Why we really need to do this first? Because testing a machine learning model on a computer is much more easier. You can simply write a small Python script using a built-in library to access the laptop or computer microphone and then process your voice directly. Sounds very simple, right? Now compare that to running the same model on a microcontroller. On a microcontroller, you would need first to connect the MEMS microphone or any other type of microphone, configure the audio peripheral, capture the raw audio, and then save it in the RAM, and then process the raw data before you can even feed it in the machine learning model. And that's the key reason why TinyML is more challenging. You don't just need machine learning knowledge to train and test a model on the PC. You also need embedded system knowledge to make the same model work on the microcontroller with limited hardware resources. Before we dive deep into the technical detail, let me first walk you through the wake-up word or keyboard spotting stack. This gives you a clear picture of how the entire system works step by step before we zoom into the implementation. The first part of the stack is the capturing real-time audio from the MEMS microphone. So we use STM32 DFSDM peripheral to sample digital microphone data. To keep the system running smoothly, we will store the audio in the ring terminal, the buffer of the microcontroller, so we can continuously capture new sample without losing the old data. The second part of a stack is frame slicing. Since the raw audio is too large and noisy for machine learning, we can slice it into a small frame, for example 30 milliseconds per frame. To avoid losing any information, we can use overlapping technique. A new frame starts every 10 milliseconds. This overlapping technique helps the machine learning model to capture smooth transition in speech. The third part of stack is feature extraction, which we use MFCC technique. MFCC stands for Mil Frequency Cepstral Coefficients. This is a technique which gonna convert waveform to a spectrograph. Each frame of audio is gonna transfer into the feature which the machine learning model can understand. With MFCC techniques, we are capturing the most important frequency pattern of the human speech. Think of this technique like compressing the audio into a voice print. The fourth part of the stack is gonna be frame buffering. Since a single frame of FCC doesn't tell us much, words are spread over time. So we combine multiple FCC frames into a 2D tensor. For example, 49 frames each with a 10 coefficient give us an input shape of 4910. Now, why 49 frame? Let's do a simple math. Suppose we analyze about 1 second of audio. With a 30 millisecond frame and a 10 millisecond overlap step, we get roughly 1000 milliseconds. If we divided this number by 20 milliseconds, we get around 49 frames. So in one tensor, the machine learning model will see about 1 second of sound, enough to recognize a keyword. Next is going to be running the model inference on the microcontroller. The MFCC tensor will pass into the model and we will see the result of the prediction. For this project, I'm going to use STM32 IoT development board, which has the one STM32L4 microcontroller and two MEMS microphones. For the sake of simplicity, I'm gonna configure just one microphone and record the mono audio. This keeps things straightforward while we are focusing on capturing clean voice data for our machine learning model. STM32 offers three common built-in audio peripherals: I2S, SAI, and DFSDM. In this video, I will be using DFSDM, which is a stand for Digital Filter for Signal Delta Modulator, since it's a preferred for working with the MEMS microphones. To put it simple, the audio peripheral on STM32 microcontroller work like a translator. In our case, they translate PDM signal into PCM signals. You might ask, what is PDM and what is PCM? Why are we going to translate these signals to each other? PDM, or pulse density modulation, is a 1-bit audio stream used by many MEMS microphones. PCM, or pulse code modulation, is a standard digital format that computer and audio system understand. The challenge is that PDM cannot be used directly. To make it usable, it needs to be reduced with some decimated technique and clean up with some filtering technique. That is exactly what the audio peripheral like DFSDM does. DFSDM peripheral takes the raw PDM data and turn it into the clean PCM that we can record, process, or playback. Let me walk you through the block diagram of this process in more detail so you get a better understanding of DFSDM. First, a person speaks, generate an analog voice waveform. This waveform is picked up by a MEMS microphone, which is connected to the STM32 DFSDM input. The first block is the PDM receiver, which receives a high-speed PDM signal and pass it to the filtering section. STM32 uses the sync filters by default, a type of low-pass filter. You can choose the filter order. It is recommended to use order 3 to 5 to achieve optimal performance. The main goal of the filtering section is to remove high-frequency noise from the audio signal. Then the signal will pass to the decimator section. In STM32 DFSDM, the decimator takes the high-frequency filter output and reduces its data rate by a factor called oversampling ratio. This process converts a fast, noisy stream into slower, clean, high-resolution digital data that is ready for processing. Finally, the output of all this section is a PCM signal. In our project, we will use a 16 kHz sample rate and save it in WAV format. This forms the first step of our keyboard spotting stack, the data preparation stage. Here's a simple workflow of this project. We will use an STM32 development board to capture the raw audio and prepare it as a 16 kHz PCM signal. Next, we will send this data in batches to my computer, where I have written a Python script that receives this batch of data and save it in WAV format, which is ready to play. We will go through all these stages together step by step. Let's take a look at the schematic of this evaluation board to see how these two MEMS microphones are connected to the STM32 microcontroller. Here's a snapshot of the schematic. The two microphones are sharing the data and clock pins, which means they are sending audio data at the same time. But how is that possible? This is a common technique for stereo audio recording. MEMS microphones have a pin called right or left selection mode. If this pin connected to VSCC, the microphone generates valid data on the rising edge of the clock. If this pin connected to the ground, it generates a valid data on the falling edge. This way, the two microphones send the data alternately, one on the rising edge and the other one on the falling edge. Finally, the DFSDM peripheral in the STM32 automatically separate these two signals as soon as they are injected into the module. It will provide us two independent audio streams for stereo processing. As I mentioned earlier, when we use two microphones that share the same data on clock line, these create a stereo configuration. That means one microphone is set up in the left mode and then the other one in the right mode. So for each audio sample, we actually receive two data points, one for the left channel and one for the right channel. Now in our case, we are only using a single microphone. That means we will just receive the right mode data points. It is really important to keep this in mind when we are processing the data array coming from the DFSDM. So let's tease apart the STM32 DFSDM and see what is inside. I will walk you through the program overview from the MCU point of view. Here's the connection. Both data line microphones are tied to the input number 2 of DFSDM, and we are using internal clock. Now inside DFSDM, there are two key components, channels and filters. The channel handles the serial audio input from the microphone, while the filter processing the decimated data to give us usable audio samples. Let's do a quick program overview for the STM32 project we will be writing. First, our PDM microphone signal will flow into DFSDM channel 2. We will configure the channel to trigger on the rising edge of the clock. From there, the data goes into filter 0, where we will set up the filter parameter in just a moment. For reducing the load on the MCU, we will use DMA1. The DMA will take the data directly from the DFSDM peripheral and write it into RAM. Since the DFSDM resolution is 24-bit, each data point will be stored in an integer type. The DFSDM buffer size will be 1024 elements. And since each element is 4 bytes, that is how much memory we will allocate. Next, we will downsample the raw data to 16-byte PCM format. The downsample data will be written into the ring buffer, which is 4 times larger than DFSDM buffer. The ring buffer will automatically overwrite the old data once it becomes full. So we will need to carefully handle the writing new data from the start of the buffer again. After that, we will set up another DMA channel. This one will read the downsample data from the RAM and send it out over USART TX1. On the PC side, I will have a Python script running. The script will receive the incoming audio data and save it into WAV file. Once that's done, we will be able to play it back and actually hear our recorded voice. Before using the DFSDM, we need to answer some important questions. The first question is, what sample rate will be used for recording? Is it 16 kHz, 32 kHz, or 48 kHz? The second question is, what is the bit depth for each sample? For example, is it 16 bit or 24 bits? The third question is how many channels do we need? Is it mono or is it a stereo configuration? The fourth question is what is the maximum frequency of our MEMS microphone can handle? The fifth question is how are the microphones connected in our PCB? Finding the answer of these questions will help us to set up DFSDM correctly. Let's go through the question and find the right answer. The first answer is the sample rate is gonna be 16 kHz because it is suitable for low bit rate audio and speech recognition on STM32 microcontroller. The second answer is the bit depth is gonna be 24 bit since the STM32 DFSDM has a 24 bit resolution. The third answer is gonna be mono because I'm going to use only one microphone on the evaluation board. The fourth answer is the maximum frequency is gonna be 3.2 MHz because I'm using MP34DT01 MEMS microphone from ST Microelectronics, which is support up to 3.25 MHz. Here's the snapshot of the data sheet where we can see the maximum frequency. The fifth answer is since two microphones share the PDM data and clock lines and connected to the MCU DFSDM channel 2 and DFSDM clock out, one microphone sending a data on the falling edge and the other is sending on the rising edge, creating interleaved left and right data. In this part of the video, I would like to walk you through the DFSDM parameter configuration on the STM32. The first parameter is DFSDM clock configuration. The first step is configure the correct frequency that will be supplied to the DFSDM peripheral. Since the MEMS microphone has a maximum frequency of 3.2 MHz, and for this tutorial I'm using 80 MHz MCU clock. So we need to calculate the proper divider value. For the divider I'm using this formula. Frequency of the MCU divided by the maximum frequency of the MEMS microphone, which in this case is gonna be 25. Now let's get started to configure the important part of the DFSDM peripheral, which gonna be filter configuration. There are three important parameters that must be set before using DFSDM. Two of them are low pass filter parameters, FOSR and IOSR, and one output offset value called write bit shift. The filter parameter controls the decimation process of the audio signal, while the write bit shift helps scale the final output to avoid overflow. Based on the information given earlier, the value of FOSR and IOSR can be calculated using this formula. Frequency of the audio equal frequency of the DFSDM clock divided by FOSR divided by IOSR, which this value has to be matched with the frequency of the sample rate, which in our case is gonna be 16 kHz. Given the 16 kHz and knowing the frequency of the DFSDM, we can easily calculate the value of FOSR and IOSR. Let's wrap this up by putting everything together in one diagram. This way we can clearly see what is happening under the hood of DFSDM process. As I said earlier, the microphone is connected to the input number 2 of DFSDM, and the clock pin is connected to the clock output from the internal clock source. I'm gonna set the frequency of the MCU to 80 MHz. In this way, the frequency of the MCU is injected to the DFSDM module and it will pass the DFSDM divider, which we are going to use 25, and it will generate the DFSDM frequency, which is gonna inject it to the microphone, which is gonna be 3.2 MHz. As soon as the MEMS microphone receives clock input, it will start generating the PDM data, which is gonna pass to the first block of the DFSDM, which is serial transceiver. The serial transceiver will receive the PDM data and pass it to the filter section. As we discussed earlier, the filter has two components, FOSR and IOSR. By adjusting these two parameters, we are going to achieve our desired sample rate data, which in our case is gonna be 16 kHz. Here's the formula. and then the data will pass to the offset correction, which is called write bit shift. I will explain how the offset correction work in the next slide. And then the main output of this process is gonna be PCM data. Let's talk about write bit shift. What is the write bit shift and how do we choose the correct value for it? To answer this question, we need to first understand how the sync filter is configured and what the bit depth of each data sample is. In this audio recording tutorial, I wanted to downscale each data sample from 32-bit to 16-bit PCM. The main reason for this is to save memory, and for speech recognition on STM32, this reduction does not affect performance. Let's review our setup first. We set the filter over sample ratio or FOSR to 200 and integrator over sample ratio to 1. I'm gonna use the filter type fast-sync, knowing about the frequency of the DFSDM, which is gonna be 3.2 MHz, and then the target bit data is gonna be 16-bit PCM data. Before we calculate the write bit shift, let's go over a few audio signal concepts. In audio, a DC value corresponds to the steady, unchanging input. The gain of the DC of the filter shows how much a constant input will be amplified. For the DFSDM, which convert 1-bit PDM into multi-bit sample. So the gain of DC is equal to maximum amplifier the filter applied to the constant PDM signal. Let's clarify this with an example. Suppose the PDM input is always 1, which means the maximum is gonna be 1. If the filter has a DC gain of 400, after decimation, output will be 400 in digital units before any scaling. Since our filter type is fast-sync, the gain of the DC is approximately equal to gain equal FOSR multiplied to, which in our case is gonna be 400. Now let's calculate the maximum output of the DFSDM with this formula. Max output is equal to 2 to the power of 16 multiplied by gain. Because STM32 DFSDM has 24-bit resolution, the maximum value of the PCM data sample can be expressed as PCM out equal DFSDM raw output minus 1 divided by 2 to the power of write bit shift. Without shifting, the raw DFSDM output range is gonna be this. If we apply write bit shift, let's say shift by 3, we gonna dividing the raw data by 8, which we gonna downsampling the data. The purpose of the write bit shift is to scale down to avoid overflow in 16-bit storage. In this tutorial, I'm going to show you how to use DMA with DFSDM and USART to reduce the MCU workload. Think of Cortex-M core as the king of MCU. It is a smart, make decision and run the main logic, but it should not waste time on repetitive tasks. For that, it relies on DMA, which acts like a dedicated worker. The DMA is very efficient at doing one simple job over and over, moving the data between peripheral and RAM, and the other way around. Since audio recording fits into this model, we will use two DMA channels. DMA1 channel 1 is responsible to capture the bit stream from DFSDM and save it into RAM. Each data pack is an integer, 4 bytes. We use a buffer of 1024 elements. Then DMA1 channel 2 take the stored data and send it through USART1, where it is received by a Python script on the PC and save it as a WAV file. Here's the overall process. Let me walk you through the STM32 CubeIDE configuration. The first configuration is gonna be DFSDM pin configuration, where we need to assign the pin of the microcontroller to the data and clock pins. Since I'm using channel 2, so for data I'm using PE7 and for clock I'm using P9. The second configuration is the channel 2 configuration. As I mentioned earlier, for this project I'm using channel 2 and filter 0. Under computing category, we click on the DFSDM1 and choose channel 2 and configure it as a PDM SPI input and internal clock. The reason why we are using PDM SPI because in STM development board, two microphones are sharing data and clock. Under channel 2, we need to choose the type as a SPI with a rising edge. As I mentioned earlier, it's depend on how LDR pin are connected. In this tutorial, I'm using only one microphone, so the LDR pin is connected to VSCC, meaning that this microphone is sending the data on the rising edge. And we are using internal SPI clock. For the offset for now, we are setting to 0. This value need to be adjusted based on experience. And for the right bit shift, as we discussed, we are planning to shift 8 bit to the right side. For filter order, I'm using fasting filter and overlapping parameter we are setting is 1. The third parameter is a DFSDM clock and clock divider. In this project, I'm using 16 MHz MCU internal clock and I'm passing through PLL to get 80 MHz. The same frequency injected to the DFSDM module. Now we need to come up with the right divider number. Before we select the divider, we need to make sure what's the maximum frequency of our MEMS microphone. In this example, as I mentioned, since my microphone support maximum 3.25 MHz, so that we are setting 25 as the divider. The fourth parameter is a DFSDM filter 0 configuration. Under filter 0 tab, we have to choose the channel what we are going to use, which in our case is going to be channel 2. For real-time audio processing, we need to use continuous mode. For the trigger, I'm using the software trigger. We need to write a line of code to start DFSDM peripheral. And we are also enabling fast mode and DMA mode. Again, so we set the filter as a fasting filter. And for the FOSR and IOSR, as we discussed, we are going to use this formula. The fifth parameter is going to be DFSDM DMA configuration. Under DMA setting, I'm going to assign DMA 1 channel 2 to the filter 0. The mode is going to be circular because we are keep reading as a real-time data and we are saving the data from peripheral to memory, so that we have to check the memory box here. Since our data is going to be 32 bits, we have to choose word as a data type. And then the last configuration is going to be USART configuration. As I said, I'm going to use USART 1 and I'm going to set the baud rate of the serial port to 921600. And I'm going to assign the DMA to USART TX pin, which is going to read from memory to peripheral. And then the data type is going to be byte in STM32 microcontroller, sending the data byte by byte. And then the last configuration, we need to enable the global intro where we would be able to receive a callback function. Let me walk you through the C++ code which I written for this project. The first and second line is about the configuration of the filter and channel 2. This line is using the DMI assigned to filter 0. The next line is configuring USART and assigning DMA to USART 1. Here 16 kHz the frequency, and here's the buffer size of the DFSDM. And audio capture buffer is gonna be ring buffer, which is gonna be 16 times bigger than the DFSDM buffer. And I'm using the capture sample to record the audio, clamp function to make sure we are not overloading the 16-bit. Now I'm using transmit an audio frame to send the audio to the serial port. And here's the callback function. After sending the data, we enable the flag. And also here the definition of the clamp function. And then the main function is going to be capture a sample. In the for loop, we are saving the data into the buffer. And we are recording the index of the destination. And as I mentioned, since we already set the DMA for DFSDM as a circular process, we expect to receive two callback functions. First, once the half of the buffer get full, once the second half of the buffer get full, which help us to send the first half of the data, and then after that, the second half. In this line, we are enabling the DFSDM since we already set as a software trigger. And here's the while loop where we are continuously sending the data to the USART1. Let me walk you through the Python script which I'm gonna run in my computer to receive the audio data and save it as a WAV format. In a couple of first line, I include the necessary library which I need to run this code. And I connect my STM32 to port COM3, and then the baud rate has to be matched with the baud rate which we already set in the microcontroller, which in our case is going to be 291600. The sample per frame is going to be 1024, and the byte per sample is going to be 2 because we are sending 16-bit data. After saving the data, the file name is going to be receiveaudio.wav, and then the sample rate has to be matched, which we already set it in the microcontroller, which is going to be 16 kilohertz. These are the rest of the code, and here where I'm saving the file. Let's do a quick live demo. I'm gonna record a short audio clip using STM32 and MEMS microphone, and then I will save that recording data into a file and play it back. TinyML Specialization Voice Recognition. As you can see here, the Python script successfully saved the file. Let's play the audio. As you can hear, the quality of the audio is pretty decent. This confirms that we are successfully recorded audio data into the ring buffer and save it into file. In the next video, I will move on to the second and third part of the stack, frame slicing and feature extraction. See you in the next one.